Good day, class. Welcome to lecture number 8. This is the last lecture of the E-series lectures on digital image processing. And today we will continue our talk on image enhancement in spatial domain. If you remember, in previous lectures we talked about arithmetic and logic operations, subtraction, image averaging. We talked about kernels of convolution and correlation. And also we talked about average filter, like box filter and weighted average filters. Now today we will talk about ordered statistics filters. The ordered statistic filters are nonlinear spatial filters whose response is based on the ordering or ranking of the pixels contained image area encompassed by the filter. Now the center pixel is replaced with the value determined by the ranking results, and this ranking result is by some statistical operation. And the best known ordered statistic filter is the median filter. From the statistic course, you may remember median of a set is if we sort the elements of this set from higher value to lower value, from lower value to the higher value, the middle element will be the median value of that set. So what we do, we will have a mask in the median filter in image processing, and then within this mask we will order the pixel value which are covered by the masks, and the middle value will be replaced by the center of the mask. Now here in this image you can see we have an image which has been a nose, which nose has been added to that, and this nose is called a salt and pepper nose. Salt and pepper nose or impulsive noise can be easily removed by median filter. As you can see in this picture, we see the average of we see the application of averaging filter. As you see, still it's noisy, and you can see if we apply the median filter, we will already get rid of all the noises. Now this image is from the Gonzalez and Woods book, which has been referred in the slides. Now we will talk about sharpening of spatial filters. We can do the sharpening of the images in the spatial domain. In the course, we will talk about frequency domain, and we will see how we can do the sharpening of an image also in frequency domain, but we will focus on sharpening in the spatial domain. Sharpening is the operation to highlight fine details or edges or enhance the details that has been blurred. The blurring is based on the averaging in a neighborhood, which is analog to some and can be represented as an integration. Therefore, the sharpening could be accomplished by differentiation. So sharpening is opposite of blurring. In blurring we have the integration, so when we come to the sharpening we should have some difference or derivatives. So the derivative of a digital function is defined in terms of differences, because we know that in the digital form we are discrete, so we are not continuous. So a first order derivative of one-dimensional function fx can be defined as what you see in the slide. Now second order derivative can be also defined as shown in the formula in the slides. And of course we can define it with respect to one variable if the function is a function of one variable, or if the function is a function of two independent variables. We will see how we can define it. Now what we have to notice is that the first order derivative is 0 in the flat segments. In other words, if the value of the function is not changing, the first order derivative is 0, because the difference of two same values is 0. And if we have changes, in other words, if we have a ramp, it will be non-zero. Whereas in the second order, still the value is 0 when we have a flat segment. The value is non-zero at the beginning and end of a ramp. And during the ramp, the value of the second order derivative will be still 0. So let's talk about the second order derivative for enhancement. And the second order derivative that we will use in order to do the sharpening is called the Laplacian. Now, and this Laplacian is a kind of filter which is called an isotropic filter, where the response of the filter is independent of the direction of the discontinuity in the image. Isotropic filters are rotation invariant, which means that if you rotate the filter and the image, or if you filter and then rotate the image, you will get the same result. So rotating and then filtering, or filtering and then rotating, you will get the same results. The Laplacian operator, you may remember from the differential equation course, is as shown in the slides, where if we want to write it in the discrete form, we have to write it in the two forms, one with respect to x, one with respect to y. In other words, the 2D Laplacian, the two-dimensional Laplacian, can be written in this form. Now, f, x and y is the center. And when we are adding or removing one to x or y, it means we are going to different neighborhoods. So as you can see in this slide, we can eventually develop four masks. And these four masks, two of them are isotropic to the with results for 90 degrees, and the other two are isotropic for 45 degrees, where we have also the diagonal elements. Note, if we add all the coefficient value, we will get 0. Now, by using these filters, what we will get some edges, some high frequency components. Now, how we will do the enhancement is, when we are applying the Laplacian operator, the highlights or the high frequency need to be added to the image. How we will do this addition? By using this formula. As you can see, we have two steps. If the center coefficient of the Laplacian mask is negative, we will use the top formula. If the center of the coefficient of the Laplacian mask is positive, we will use the lower formula. Now, here in this image, you can see we have a picture of obelix. We are applying the Laplacian. So as you can see, it's not clear. So we are enhancing it by image equalization, so you can see the high frequencies. Now, the previous one without enhancement, we will add those values on the image, and this is what we get at the fourth image. As you can see, it's much sharper. Already you might be familiar with the concept of sharpening if you are using Instagram. It's one of the filters that we use in Instagram. Now, another first order derivative that we use for image enhancement is the gradient. The first derivative in image processing are implemented by using the magnitude of gradient. The gradient of f at coordinate of x and y is defined by two-dimensional column vectors, as we noted by gx and gy. And the magnitude of this vector is referred as the gradient. So here we see how we can calculate the gx and how we can calculate the gy. So if we consider we have a 3x3 mask, then an approximation around the center of the pixel is as shown in this formula. Now, here you will see two masks which are known as Sobel operator and can be used to implement the gradient operator. The idea behind using weight values of 2 is to achieve some smoothing by giving more importance to the center point. So the mask on the left is approximates the derivative in the x direction, and the one on the right approximates the derivative on the y direction. Here we can see an image, an example from the Gonzalez and Woods, and we are applying the horizontal operator and the vertical operator, and these are what we get. The high frequency or edges which are in the horizontal direction or are in the vertical directions. So we have here, see the output of the horizontal Sobel operator and the vertical Sobel operators. And what we have to do at the end, we have to find the magnitude. In other words, the horizontal square plus the vertical square underneath of the square root. And this is what we get as an output. Now, in today's lecture, we talk about what is the statistical order filter, and we talk about medial filter. Within the course, we will see a bit more of the statistical filters. We have seen how Laplacian and gradients are being calculated and how we can use them in order to enhance an image. Now, as I mentioned, this was the last lecture of this E-series of digital image processing. In the course of digital image processing, we will start to pick up the topic right after this lecture, which means that we will start to talk about image enhancement in frequency domain. And after that, we will talk about color images, and later we will get back to this spatial domain and we will talk about a few more functions and filters. I hope that you enjoyed this E-series of digital image processing, and it gives you some slight background of what digital image processing is. And by now, you have to be able to actually implement some of the digital image processing tasks. And now, maybe when you are using your Instagram, or maybe when you are using your Photoshop, you will have a better idea of how some of the filters are working. Have a nice time. Be seeing you in the class.